Welcome to the today's class. Today is lecture number 2 in unit number 4. Okay, so examples of SM charts that we will see. Previous class we have seen the basics of SM charts that we have seen. So what is the theory behind the SM charts? Why the SM charts came into existence that we have seen? As the complexity of the circuit is increases, or maybe number of inputs are increases, state graph or state diagram is not the best possible method. So therefore we have gone for the more abstract way that we can give the information about the operation or application by using the SM charts. Okay, so for example, today we are going to look at, if you have an SMS state graph in your hand, then how can we convert it into SM chart? Let us see now. Okay, the conversion of state graph into SM chart. We'll take one example. For example, let me paste here. Okay, for example, you take this as an example. We have a state diagram there. Okay, so the state graph is shown here. It's a state graph. So it has got the state S naught. At that particular state, we have given SA. Okay, normally when the output is depending upon the present state only, then that particular state graph is called Murray FSM. Murray FSM. So therefore, it is the state graph is belongs to the Murray FSM. In the previous class, I told that Mealy FSM. Okay, so Mealy FSM that we have seen in the last class. So in this class, we are talking about the Murray FSM. So the Murray FSM state that the state, for example, S naught we are considering. Okay, so for that particular state, we have to define the output instantaneous to that one, or I can say that the state defined with the output value. So therefore, if this is the notation, if you follow, this is called Murray FSM. Okay. So otherwise, for example, if it's not only the consideration is considered, and the output is depending upon the input condition, then it is called Mealy FSM, right? Okay. So now if you have this FSM, then how do we convert it? Okay, as I mentioned that the state is represented in FSM, sorry, in SM chart as box. Okay, something rectangular box that we have to consider, and its output is defined by SA. Okay, so this is we should know. Now, depending upon the X value, for example, here is the X is the one and Y is the output. Okay, therefore X is that input, Y is here is output. So it is a conditional output. You can say very important to you have to write it. Two outputs that we can observe. Okay, here is for example S2. For example, S naught divided by Z naught. Here the output is not conditional output. It's not a conditional output. Okay. But whereas here, if you see here in this way, or maybe some other way, for example, something here 0 by 0, for example. So here is the output. This is the output Z naught. Here is the output is actually conditional output. It's a conditional output. That means when the X is true or false, then only when condition is satisfied, then only the output will come into existence. Otherwise, the output is not existed. Therefore, the output can be two types: conditional output, unconditional output. Okay. So here, unconditional output I have written here. So this is what it says that. And depending upon, if X is equal to 1, for example, X is 1 means this is the 1. X is equal to false, 0 అయితే ఏమవుతుంది, it should be remains in the same state, right? So that's what happening here. This should be remains in the same state. Okay, if x is true, it moves to the next state called S1. So therefore, if it is true, it goes to the next state called S1 with output is equal to ZB, right? Now, so if you are there in the S1 state, again we need to think about what if x is equal to 0, what if x is equal to 1. If x is equal to 0, it has to go to the previous state. If x is equal to 0, it has to go to the previous state. So previous state, something like this it is going, right? If x is equal to false, sorry, x is equal to true, then it has to go to the next state, something like this. So it has to go to the next state called S2, right? Clear? Now again, if you are there in the S2 state, if it is a 0, if it is 0, sorry, if it is 1, then it has to go to, it should be remains in the same state. If it is remains in the same state, right? Better I to write it in this one. Remains in the same state. If x is equal to 2 with a conditional output, you can observe here, if x is equal to 1 and z must be 2, z2 is available. That means the conditional output. With z is equal to, it should be remains in the same state, right? If x is equal false, for example, x is equal false, then with the output z1, it has to go to the initial state. So therefore, if x is equal to 0, so with this output, it has to go to the previous state. Clear? Oh, what is this? Fine. I hope you can understand. Once we have a state diagram in your hand, it is possible to convert into state machine chart. Okay. And some additional things are also you can see here. It is 0 0, it is called 0 1, it is called 1 1, for example. This is called state assignment. State assignment. So that means that how many states are the 3 states are there. So therefore, if you want to identify these 3 states, S0, S1, S2 that we are using, but in binary representation we have to identify these things so that it is possible to convert into a circuit. So if you have a 3 state, means 2 bits are required, 0 0 0 1 1 0 we normally use, but for the sake of better hardware realization, instead of 1 0 1 1 the people will use. Okay, therefore the state assignment is also one method by which we can reduce the complexity of the circuit. That means hardware cost will reduce by assigning properly the value of this one. But conventionally we use 0 0 0 1 1 0, but only one bit change of state assignment is the best suitable method. Okay, so okay, that is for the sake of simplicity I'm telling you that. So that's what we can observe. Another one is links that we can observe. So okay, this is the one link, this is the link that normally is. So this link concept we will see later on. It's not advisable to talk about here. Okay, so this point out here is that the conversion of the state graph into a SM chart. How can we do? That's what we have learned so far. Okay, now let us consider one example, very important example. How do we generate the state diagram? Sorry, state SM chart for a particular application? Let us consider a digital circuit is called multiplier. Okay, multiplier. So the 4-bit multiplier, let us consider. So therefore I have a device here, for example. Okay, I have a device. I have a device here. So one data is something like this, second data, say 4-bit size data of A, 4-bit size of data of B is required. So what is the output that we can get? Actually the product we'll get, right? Product is an output. Okay, so what is the size of this output? If two 4-bit numbers are multiplied, what is the size we'll get? 9. So 9 is the size that we'll get. Okay, so since I want to perform this operation based on one start signal, Whenever the start signal is there, then only the multiplication has to be done. Once the final output is reached, then I want to see one output called done output. So these are the two additional signals that I'm giving to this one. Okay. Since any circuit is normally in almost in a digital circuit, all these things are clock dependent nature that we are interested on. Okay. Therefore, we want to operate this kind of information based on a clock signal. Okay. So that's the reason why two additional signals also we consider, that is called a clock signal and reset signal. For the sake of simplicity, I'm not going to introduce a reset signal. Okay, but it will be there. But we are not interested in this one. But these are the input output information related to uh, the multiplier, right? Are you agree with me? It's a multiplier. Okay. Now, how do we look at this multiplier? Okay. So generally, whenever we want to realize this multiplier, the people will use two methods. One way, a very essential way that the people will use. One way is called convert this entire digital system into a control path and a data path. So every digital system, normally considered this is the multiplier digital system. We use a control path. Next one is called data path. So data path unit, we can call it as module or unit, whatever it may be. It is also a unit. So this is what a digital system is look like, right? So the question is that what is the responsibility of the control unit? What is the responsibility of the path unit? So normally data path unit consisting of all the operation related hardware. For example, multiplication related hardware. So registers are required, flip-flops are required, addition is required. So different blocks will be available for the data path unit. At what time, which operation has to perform, that is decided by the control unit. Therefore, the sequence of operations are performed based on the control unit information. So that means the control unit must generate the necessary control signals to this one so that the operation will be performed by the data path unit. Right. So that's what we can understand. So, okay, keep this one in your mind. Now, very important thing is that normally we use FSM, normally we use SM charts here. Normally we use SM charts to realize the control units generally. Okay, how can we do this one? Let us now look at. First, before going to this differentiation of all these things, first we should know what is the multiplier, how multiplication will be done from the top operation. How do we generate the state graph? From the state graph to state diagram, how do we, so from state graph to SM chart, how do we develop? The SM chart to hardware, how do we transfer? This is a simple multiplication expression. For example, you can study here. Okay. So here you see, observe very carefully. Just you can observe this. So I want to multiply the two numbers. One is the 13. One is 13. Next one is Now see here, the multiplication is done here. So one by one, bit by bit, that we can do one with all these bits. Okay, so this is what
Sir, screen sharing is off.
network is disconnected. Okay, so here you observe carefully. So we have to identify we have to multiply this normal multiplication. One bit is multiplied with all these bits. So therefore we will get here. So 1 into 1, 1, 1 into 0, 0, 1 into 1, 1, 1 into 1, 1. Something like this. So we take another bit and we get this one. Okay, multiply this one. So therefore, instead of adding, do all the things left by left, left by left, just after completion of the two things, just add all those things. Okay, so normally ఇంతే కదా చేసేది మనం 1 1 0 1 వచ్చింది. Next 1 0 1 1. నెక్స్ట్ వన్ ఇస్ ఇక్కడ వస్తుంది మనకు 0 0 0 0. నెక్స్ట్ ఇక్కడ వస్తుంది 1 0 1 1. ఇది మల్టిప్లై చేస్తాం. ఓకేనా? సో దీస్ ఆర్ ఆల్ కాల్డ్ పార్షియల్ ప్రొడక్ట్స్ అంటాం మనం. దీస్ ఆర్ ఆల్ కాల్డ్ పార్షియల్ ప్రొడక్ట్స్. Okay, so instead of doing something like this, after two things are completed, they have added here. Result is something like this. Now the third one we have to multiply and add those two things also, and again third one and do this one. This is called final product. Final product. So this is the basic operation, or I can say that the conventional multiplication operation. Okay, so this is not the best method to implement the circuit. Okay, it has got some drawbacks because of the more number of devices will more number of the hardware cost will be very, very high if you are implementing this method. Okay, so therefore an alternative method, so that is called add shift method. Alternative method, which is nothing but add shift methodology. Another method is based on add shift. Okay, so in this add shift method, what we do, something like this we have to perform. Okay, this is the method normally we use. I will explain this how it will work. Okay, I hope this is visible, right? Fine. So the same thing that I'm doing with the help of add shift methodology. Okay, what we do, so we have to consider an 9-bit register. Okay, this is a 9-bit register. So what that means, that we have to consider the 9 bits first initially. Okay, 9 bits, that means whatever the size of the product value is there, that product value for the product, how many bits are required, those many number of bits that we have to consider. Fine. Now we have to load, very importantly you have to understand, because we are going to write the Verilog program for this one also. Okay, so we have to load the multiplicand information at this point, sorry, multiplier information at this point, right? What we have to do, it is a multiplier. So ms multiplier. So LSB positions are, last 4 LSB positions are filled with multiplier. Clear? That's what I have done. Okay, now what I have to do, so after the fourth bit is completed, then I need to introduce multiplicand. I need to use multiplicand. Okay, so whether I need to add, so what I have to do is that first loading the value. So load చేస్తున్నాను, తర్వాత ఏం చేయాలంటే last position of the LSB bit you have to consider. Last position of the LSB bit we have to consider. If that value can be called as m అనుకోండి, for example, if m is equal to 1, what do you mean by the 1 here? It is the LSB of multiplier, or multiplier, or I can say that simply we can say that the product term. అర్థమవుతుందా? Okay, so if it is 1, we have to add the multiplicand to this value. Okay, if this is 1, if m is equal to 1, then I have to consider what I have to consider, multiplicand I have to consider, and add this multiplicand to this product value. Now if I add this one, what is happening here? Tell me. 1 is already 1. Okay, 1 is 1. Okay, 1 is 1. Fine. Next, 1 is again, 1 is added here. So 0 means 0. 1 means 1. Here is what is happening, 0 plus 1. What is the value? 1. 1 here, 1 here, 0 here, 1 here. What about here? 0 plus 0, 0. 1 plus 1. So 0 plus 1, 1. 0 plus 1, 1. 0 is again here 0. This is how the result is. Okay. Now, again we have to check the one. Whenever we are adding the multiplicand to this one, immediately after we have to perform the shifting operation. We have to perform the shift operation. So what is happening here? 0, 1, 1, 0, 1, 1, 0, 1, 1 అనేది shift చేస్తే ఏమవుతుంది? We have to shift towards the right side. So here this is the vacant position. This come here. అంతే కదా? This come here. This is the 1, 0, 1, 1, 0, 1. ఇక్కడ ఉన్న 1 పోతుంది, ఇది పోతుంది. But what is this one? This value is filled with 0. So this is what the information that we have to do. Okay, so therefore that is what happening here. 0, 0, 1, 1, 0, 1, 1, 0, 1. Clear? So therefore what I have done, I have added the multiplicand, and once the result came, I have to shift towards the right side. Okay, what I have done here, the procedure is first to add multiplicand, not 1, we should not do it. As soon as the multiplication is added, multiplicand is added, and we have to, the first step, second step, the third step. First step in I'm sorry, the network is a problem. Okay, please try to understand. Okay, so there is a serious network problem here. Actually, I sat in my staff room, but signal is not that much good. But anyway, please try to understand. Is it clear? So what is the first step? First step is insert the multiplier to the product. LSB positions are filled with the multiplier information. Second one is, depending upon the M is equal to 1 LSB position, we have to add the multiplicand to the product. The third one is shifting. As soon as the addition is there, then shifting has to perform. So far, so good. Okay. Now this point, up to this point, we don't have any problem. Now again, we have to think about, after the shifting, we have to think about M value. Okay. If M is there, again, what we have to do? What we have to do? So we have to add again 1. So that means multiplicand, we have to add it here. Okay. And at these positions, and we have to add all these things. Therefore, this becomes, what the value of this becomes? 1, 0, 1, 1, 1, 1, 0, 0, 1. Clear? Now, as soon as the addition is completed, we have to go to the shifting. What is the shifting value? The shifting value is, this is 1 here, this is 0 here, 0, 1, 1, 1, 1, 0. Vacant position is filled with 0. Clear? Now again, we have to consider that m value. M is 0 here. If m is 0, don't do addition. Don't do addition, just simply shifting has to happen. Okay, therefore the shifting has to perform here 0. So therefore the shifting is here 0, 1, 0, 0, 1, 1, 1, 1. So vacant position is filled with 0. Again you find that m value is equal to 1. Okay, so therefore what is happening here then again? So whenever you find the 1 here, again we have to add 1, 1, 0, 1. So that addition has to perform. This 1, 1, 1, 1, 1, 0 plus 1, 1, 0 plus 0, 0. 1 plus 1, 1, 0 అవుతుంది. ఇక్కడ 0 వస్తుంది, ఇక్కడ 1 వస్తుంది, అంతే కదా? All this 1 is 0, it becomes 1. If it becomes 1, right? As soon as the addition takes place, we have to do the shifting. Here is the 1, here is the 1, 0, 0, 0, 1, 1, 1, 1. Filled vacant position is filled with 0. So this is what my final output. Okay, so this is the same as that of this one. The question is that how many times I have to do this one. Okay, so therefore you can simply here is observe that the dotted line they have mentioned here. Okay, so the dotted line. So this dotted line, what it says that so once we have added there, then you find 4 lines here, right? Then we have to shift once. Once the shifting is performed, one shifting is performed there. One shifting is performed there. So the second time, once the shifting is performed, that means how many shifts that we are doing here is the first shift, second shift, is the third shift, and this is the fourth shift. So therefore the 4 shifts that I have to do, okay, I have to do the 4 shifts. That I can simply say that blindly I can say that how many number of bits are there for the multiplicand, those many number of times I need to do the shifting. The blind notation. The blind notation is that how many number of multiplicand bits are there, those many number of times I have to do the shifting. Okay, so that's what we can clearly observe all these things. Okay, so for the sake of simplicity I'm removing all these things, something like this. Adotnaya? Clear?
Yes, sir.
Now, so this is what we have to do. So therefore the total multiplication operation based on the add shift is something like this. First we have to load what I'm reminding, again summarize this one. First we have to load and we have to add the multiplicand based on m value, and I have done here. And immediately after the addition, shifting has to be performed. Once the shifting is addition is completed, shifting is completed, again depending upon the value I need to add or shift I have to do. Okay, so therefore m decides either addition of multiplicand or shifting. Sorry, multiplicand and shifting, both shifting, or only directly shifting is required. Okay, m decides that one. We have to understand very carefully. Okay, fine. Now let us try to draw the state diagram for this one. Okay, so now we are not going to do the directly to the state SM chart directly. Better first you draw the state diagram and then we'll look at that one. Okay, so let us write state graph of multiplier. Okay, state graph of the multiplier. Okay, better you have to consider the state graph of instead of saying that multiplier control unit. Multiplier control unit. ఇప్పుడు చూడండి, ఇక్కడ నేనేం చేస్తానంటే ఆపరేషన్ చెప్పాను ఇక్కడ. సో ఈ ఆపరేషన్ అనేది నార్మల్గా ఏం చేస్తుందంటే డిపెండింగ్ అపాన్ ద ఎం సిగ్నల్ మనకి ఆపరేషన్ యూ కెన్ అబ్జర్వ్ దట్ హౌ డు వి అవర్ మెయిన్ ఫోకస్ ఇస్ దట్ డిజైనింగ్ ఆఫ్ ద కంట్రోల్ యూనిట్. మెయిన్ ఫోకస్ చేద్దాం. తర్వాత డేటా పాత్ యూనిట్ ఎలా డిజైన్ చేద్దాం, లెటర్స్ ట్రీ లెటర్ ఆన్. సో ఎస్ఎం చార్ట్ డిజైన్ చేద్దాం. ఎస్ఎం చార్ట్ ఫర్ ద కంట్రోల్ యూనిట్, ఎస్పెషల్లీ ఫర్ ద కంట్రోల్ యూనిట్. So what we have to do for the control unit. So that means that we have to consider a control unit something like this. So what it has to provide, ఒకసారి మీరు అబ్జర్వ్ చేస్తే మీరు ఫర్ ఎగ్జాంపుల్ స్టార్ట్ అనే సిగ్నల్ వచ్చింది, మల్టిప్లికేషన్ స్టార్ట్ చేద్దాం. ఓకే, వాట్ ఇట్ హ్యాస్ టు ప్రొడ్యూస్, యాడ్ అనే సిగ్నల్ ప్రొడ్యూస్ చేయాలి, ఎడిషన్ జరగాలి, యాడ్ అనే సిగ్నల్ ప్రొడ్యూస్ చేయాలి, నెక్స్ట్ షిఫ్ట్ అనే సిగ్నల్ ప్రొడ్యూస్ చేయాలి, అంతేనా? ఓకే, వన్స్ ద మల్టిప్లికేషన్ ఇస్ కంప్లీటెడ్ డన్ అనే సిగ్నల్ ప్రొడ్యూస్ చేయాలి. Okay, so these are the two additional things that I am doing here, but I did not mention anything about in this operation, but these two things are also there. Okay, no need to mention in this operation. Okay, of course the start signal is there, then only the things will be happen. Once the multiplication is there, only the result will be taken as a consideration. Okay, now so for this one we need M signal, right? For this we need M signal. Of course we should know that load signal also must be happen. Load signal also has to generate. Okay, depending upon the M signal, either addition or shifting has to be done from. Okay, initial because of the start signal, load signal will be happen. I think better to write it here. ఇప్పుడు స్టార్ట్ చేసాను అనుకోండి, లోడ్ సిగ్నల్ జనరేట్ చేయాలిగా, అంతేనా? లోడ్ సిగ్నల్ must be generated. So what do you mean by the load? That means LSB positions of the product is filled with multiplier. That is what meaning of the load. So therefore load signal has to be generated. Load. Okay, depending upon M signal, add shift or add shift has to be performed. Once everything is completed, done signal has to be generated, right? Okay, so that means that whenever I have the circuit, the operation something like this, I have to segregate, I have to differentiate a particular diagram or a particular operation as a control unit information. So this is how I am taking the control information something like this from the operation. Okay, as simple as that. So now we have to apply to this particular data for these signals. According to this one, it will perform the things. Okay, so our main focus is that we have to generate the control unit. Okay, now so how do we do this one? So for sake of simplicity or reducing the time, I'm using the same graphs here. Okay, and paste, copy and paste here. We can draw it here, but for the sake of lack of time, I'm doing this one. Okay, okay, fine. So here let us consider our focus is that we have to generate the state diagram. Okay, now for example, it is also normally the control unit is a sequential circuit. Okay, normally control unit is a sequential circuit. Sequential circuit. So for every sequential circuit, what the information will be there? It has got a combinational block, and there is a memory element. Memory. All together will be considering this one. Therefore, the control unit is actually consisting of a control unit is actually a sequential element. Okay. So something like this, and then we combine this one and this one. So therefore, if it is a sequential circuit, obviously the state of the system will be we can define the state. That means the content available in the memory. Okay. So therefore, we consider it as S0 is the state of the system. For example, okay, you are there in this particular state. Now, if the start signal is not there, ST stands for start signal. For example, start signal is not there. And the operation perform cheyoddan cheptunna anamata. You must be there in the same state. Don't change anything about don't change the content of the memory. That means there is a start signal here. For example, there is a start signal here. If the start signal is equal to 0, don't do anything. Okay, let it be keep quiet like that only. Fine. For example, start signal is there, so ST signal is there. So what has to happen? Load must be generated. Okay, load output must be generated. Okay, so whenever the start signal is equal to 1, it has to generate the load signal. Okay, what do you mean by the load? Ante em jarugutundane tarvata sangati, but the load ane signal ne generate cheyala. Okay, that will be the active signal. For example, if naku ఒక రిజిస్టర్ ఉంది, సో రిజిస్టర్ 8-bit రిజిస్టర్ ఉంది, సారీ 9-bit రిజిస్టర్ ఉంది. ఒక లోడ్ సిగ్నల్ అనేది ఎక్కడికి వస్తుంది? యాజ్ వీ హ్యావ్ సీన్ ఇన్ ప్రీవియస్ క్లాసెస్ వీ హ్యావ్ సీన్ ఎవ్రీ రిజిస్టర్ ఆర్ ద కౌంటర్ హ్యాస్ ఎ లోడ్ ఇన్ఫర్మేషన్. సో లోడ్ అనే ఎనేబుల్ సిగ్నల్, లోడ్ అనేది ఒక ఎనేబుల్ సిగ్నల్ ఫర్ ద రిజిస్టర్. ఈ ఎనేబుల్ సిగ్నల్ రాగానే లోడ్ అనే ఆపరేషన్ జరుగుతుంది. ఎట్లా జరుగుతుంది? ఆల్ దిస్ పొజిషన్స్ ఆర్ ఫిల్డ్ విత్ మల్టిప్లైర్ ఇన్ఫర్మేషన్. అంతే, యాజ్ సింపుల్ యాజ్ దట్. So therefore my requirement for the requirement for the control unit is generating the load signal. Okay, I hope you understand this point. Next, now the next point is, now start signal is true. That's the reason why we enter into the next state called S1. Okay, because the flip-flop content will change automatically. Now depending upon M signal, if M signal is equal to true or M signal is equal to 1, what has to happen? Add అనేది జరగాలి, యాడ్ అనే సిగ్నల్ జనరేట్ చేయాలి. ఓకే, సో హియర్ దే హ్యావ్ మెన్షన్ ద నేమ్ కాల్డ్ AD. AD stands for add. So therefore if M is true, go to the next state called S2. It is called S2, right? But it has to provide the output is add. There may be a chances that M is not equal to 1. M 0 కూడా అవ్వచ్చుగా. If M is equal to 0, maybe the possibility we have defined M is equal to 1, M is equal to 0. Sorry, I'm sorry, before going to the M is equal to 0, after completion of M is equal to 1, immediately it has to do the shifting operation, right? It has to produce the shift operation, but no need to change, no need to verify any condition. So therefore, after the shifting operation is performed, it has to go to the next state called S3 state. అర్థమవుతుందా? అంటే మనం ఏం చేసాం, M is equal to 1 అంటే యాడ్ జరగాలి, షిఫ్ట్ జరగాలి, రెండు జరగాలి. సో therefore what I have to do, so from S1 స్టేట్లో మీరు ఉన్న వాళ్ళు S2కి వెళ్తారు, అండ్ వితౌట్ చెకింగ్ ఎనీథింగ్ షిఫ్ట్ ఆపరేషన్తో M అయితే యాడ్ అవుతుంది, దెన్ వీల్ హ్యావ్ టు గో టు ద S3 స్టేట్ అవుతుంది. సో దట్స్ వాట్ హ్యాపెన్. 2 states are required for that one. So the state is always says that addition operation చెప్తుంది, M is equal to true అవ్వాలి, and addition has to be produced there. I don't want to consider anything about M, but I want to consider only the shifting operation must be performed. I information. Okay, so therefore this is what happened. So what if M is equal to 0 at this one? And only shifting is జరగాల్సింది కదా. So therefore it has to do the shifting operation. So therefore it has to go back to directly to this state. Okay, అంటే ఈ S2 స్టేట్కి వెళ్ళాల్సిన అవసరం లేదు. ఎందుకు? బికాస్ ఎడిషన్ ఆపరేషన్, shifting operation that will be done at the S3 state, right? That's what we can do. So therefore this is completed. For 1 bit it is completed. For 1 bit it is completed. For the second bit, this is what we can see. Same thing will be repeated. అంతే కదా. If M is equal to 1 అయితే ఈ స్టేట్ S4కి వస్తుంది, immediately shifting జరుగుతుంది. లేదు అంటే డైరెక్ట్గా M వస్తుంది. So this is for the second bit. This is the second shift of operation. Similarly, here is the third bit. There is a third bit, right? Similarly, the same thing happened for this one also. This is a fourth bit. Once everything is completed, go back to the initial state with the done output. With the done output. Agreed? Clear? So depending upon the, therefore it is generating. So what it has to generate? Load signal generate చేస్తుంది, అలాగే షిఫ్ట్ సిగ్నల్ జనరేట్ చేస్తుంది, అలాగే యాడ్ సిగ్నల్ జనరేట్ చేస్తుంది, అలాగే డన్ అనే సిగ్నల్ కూడా జనరేట్ చేస్తుంది, రైట్? సో హౌ మెనీ స్టేట్స్ దట్ వీఆర్ యూజింగ్ హియర్ నౌ? 1 2 3 4 5 6 7 8 9 10 స్టేట్స్ దట్ వీఆర్ యూజింగ్. సో ఇక్కడ 10 స్టేట్స్ ఉపయోగిస్తున్నాం. 10 స్టేట్స్. వాట్ ఈస్ ద సైజ్ ఆఫ్ ద మెమరీ ఎలిమెంట్స్? హౌ మెనీ మెమరీ ఎలిమెంట్స్ దట్ ఐ హ్యావ్ టు కన్సిడర్? ఎనీ గెస్? 2 bits తీసుకున్నాం అనుకోండి 4 స్టేట్స్ చేయగలం. 3 bits తీసుకున్నాం అంటే 8 స్టేట్స్. 4 bits తీసుకున్నాం అనుకోండి దెన్ 16 స్టేట్స్. ఓకే, అఫ్ కోర్స్ 8 స్టేట్స్ అనేది సఫిషియంట్ కాదు కాబట్టి దెన్ we have to go for 4 states. Therefore we have to consider for this one is 0 0 0 0 state assignment. This is called 0 0 0 1 state assignment. 0 0 1 0, something like this. We have to give this one. So can you define what is the size of this one? It is a 4-bit size. Please remember, it's a 4-bit size if you consider the state graph. Okay, is there any other alternative way to reduce the number of states? That's the question. Okay, So therefore, alternative way to reduce the number of states. Alternative way to reduce the number of states. Okay, yes, it is possible to reduce the number of states by divide the control unit. For example, we have a control unit here, right? Control unit by two sub blocks, something like this. One block is only meant for add shift control, and by using the counter, it is possible. How do we do this one? We'll do this one. So how many shifts add shifting has to be performed? That is decided by the shift information. So if you give the shift information to this one, and it generates some variable called k. So depending upon the k value, I can stop my simulation. So I can stop my multiplication. How do we do this one? For example, as everybody knows that, then 4 bits as size of the multiplier is 4 and multiplier. The size of the multiplier is 4 bits and 4 shift it has to perform. Ante kada? That means the 4-bit counter is sufficient. Sorry, 2-bit counter is sufficient. 4 counts it can perform. For example, first shift has happened, so it is counting it to 0 0. Ante kada? For example, second count ayindi, then 0 1. Third count ayindi, 1 0. Fourth count ayindi, 1 1. So immediately fourth counts are completed, then it generated the k is equal to 1. So that means we can stop the simulation. We can stop the multiplication. Okay, therefore depending upon the how many times ST signal is active high, we have to give that information to the counter. Counter, once it reaches to the maximum value, it can stop the multiplication. So this information we are going to consider in order to reduce the number of states. Right? 0 0 0 1 1 0 1 1. So maximum. If maximum, then k is equal to 1. Okay, so let us do this one in an effective manner with the help of diagram. So I can draw it all these things, but for the lack of time, I'm doing this one. Okay. So this is the idea behind this one. So as I mentioned that we have add, shift, control, and counter. So depending upon the shift information, the counter has to generate the k value. Okay. So generally we do here. So let us consider this one. If you're there in the S0 state, start is not there. Therefore, you are there in the remain state. The output is also 0. If ST is 1, load signal has to generate. It will go to the S1. Only M we need to consider. Okay. So if you're there in the S1, if M is not there, M dash stands for M is equal to 0. M dash stands for M is equal to 0 and the meaning. M లేకపోతే ఏం చేయాలి, షిఫ్ట్ జరగాలి కదా. So for the shifting S1, I am meant for shifting operation. S1 is meant for shifting operation. Right? Next, what we have to do at this point, M may be 0, M may be 1. Okay, suppose if M ikkada ee state అయిపోయింది, ఈ స్టేట్ తాలూకు M is equal to true అయినప్పుడు ఇక్కడ రాసాను, false అయితే ఇక్కడ రాసాను, true అయితే ఇటు వెళ్ళిపోతుంది. It enter into the S2 state with the add signal. Once addition is completed, immediately it has to perform the shift operation. This state is meant for shifting operation. Right? So therefore, S1 is meant for shifting. Okay. So therefore, when I enter into the S2 state, for example, so when S1, if you are there in the S1 state, yet M came into existence as logic 1, then again it has to go to S2 state. So S2 దగ్గర immediately గా మళ్ళీ ఏం చేయాలి, షిఫ్ట్ జరగాలి కాబట్టి S1 కి వెళ్ళిపోతుంది. Therefore, no need to take another state, something like this. In the previous చూసాం కదా, సో ఇట్లా వెళ్ళాల్సిన అవసరం లేదు. సో షిఫ్టింగ్ ఆపరేషన్ కోసం అని చెప్పేసి ఇక్కడికి వెళ్ళాల్సిన అవసరం లేదు. You fix the S1 as an this one, and you find M is equal to 1, remove this one, come back to this one. So don't go for this one, just here and keep it here itself. So therefore we can remove this state. So like this we can remove here also, like this we can remove here also. Okay, so therefore we have to change the information in that way. But how best way that we can do? So if I'm doing the same kind of thing, M ఎప్పుడైతే 1 వస్తుందో అప్పుడు యాడ్ జరుగుతుంది, షిఫ్ట్ జరుగుతుంది. M ఎప్పుడైతే 0 అవుతుందో షిఫ్ట్ ఆపరేషన్ జరుగుతుంది. This process is repeated. Then we have to conclude somewhere, because after the 4 multiplications are there, the multiplication must be stopped. So we are going to take the help of K now. Take the help of K help. Okay, from the counter we can, as simple as that, we take the help of K means that counter help that we have to consider. Okay, so after 4 shift, the shifting every time shift jarugutune untayi kada, 4 shift ayipongane ఆపేసేయండి multiplication అయిపోయినట్లు అని చెప్తున్నట్లు. Okay, so for that one, so we are going to introduce the new concept called K. Okay, so when M is equal to 0, shift has to perform. Meanwhile we have to add K dash also. So the K dash is also meant for K is equal to 0. That is what the meaning. Okay, so therefore as long as K is equal to 0, as long as K is equal to 0 means that it is not reached to the maximum count, right? So as long as K is equal to 0, addition జరగాలి, shifting జరగాలి, లేదంటే shifting ఒకటే జరగాలి, అంతే కదా. So that's what we can do. So therefore now if we are there in the remain same state, for M is equal to 1 అయినప్పుడు then we'll take the S2 state. If M లేదు, sorry, M అయిపోయిన షిఫ్ట్ జరగాలి, కాబట్టి మనం ఏం చేస్తున్నాము, సో షిఫ్ట్ అనేది జరుగుతుంది, బట్ వీఆర్ గోయింగ్ టు యాడ్ విత్ K డాష్. ఓకే, సో ఇక్కడ కూడా మనం K డాష్ కూడా పెట్టవచ్చు ఇక్కడ. సో therefore K dash comma M comma by add and రాయొచ్చు, there is no issue at all. But no need to check that one, because we enter into this S2 state provided that we have K is not there. Okay, so the K is not there, not necessary. But ఇక్కడ ఏం చేస్తున్నాం మనం, సో ఇన్స్టెడ్ ఆఫ్ వేకెంట్ పొజిషన్స్, వేకెంట్గా మనం ఇట్లా పెట్టకుండా మనం ఏం చేస్తున్నామంటే, సో వీ కెన్ సే దట్ ద K is introduced here, K dash is we are introducing here. That means K dash is introduced చేసామంటే that means it is not reached to the maximum count. Okay, fine. Now we are there in the S2 state. ఫర్ ఎగ్జాంపుల్ ఈ స్టేట్లో కనుక, అంటే ఈ స్టేట్ ఈ రెండింటి కేసులు కూడా K dash అనేది కూడా వస్తుంది, K dash. బట్ వాట్ ఇఫ్ K is equal to 1? What if K is equal to, that means this is the one, K is equal to 1. K is equal to 1 meaning ఏంటి, maximum count reach అయినట్టు, అంటే maximum counts అన్ని కూడా అయిపోయినట్లు. That means that is we are going to use an extra state called S3 state. Okay, so therefore what is this one, we can say that it is the last and final stage, last or final state అంటాం. ఓకే, K కనుక 1 ఉంటే, K కనుక 1 లేకపోతే ఇదే లూప్లో తిరుగుతూనే ఉంటుంది అనమాట. సో నాట్ దిస్ లూప్, సో ఈ లూప్లో తిరుగుతూనే ఉంటుంది, అర్థమవుతుందా. యాజ్ లాంగ్ యాజ్ K is equal to 0, S1 S2 it will be remains the same thing. Whenever you find K is equal to 1 at this state, it will come to this one. Okay, for example మీరు S2 స్టేట్లో ఉన్నారు, S2 స్టేట్లో ఉన్నప్పుడు కంపల్సరీగా అది ట్రూ అవ్వచ్చు, ఫాల్స్ అవ్వచ్చు కదా. మీరు K is equal ఫాల్స్ అయితే ఇక్కడ రాశారు, బాగానే ఉంది, వెళ్ళిపోయింది. K is equal to ఫాల్స్ అయితే S1కి వెళ్ళిపోయింది. K is equal to true means it has to go to some other state, means dumb state అనే కదా. As long as K is equal to 1, it has to come to the final state, that's all, there is no issue. Okay, so therefore we have to, once again we have to shift the information and come back to the original position. So ఇక్కడ ఏం చేసిందంటే, clear this you should understand what we are doing here. If K is equal to 0 means these are the two things that will be there. ఇప్పుడు ఇక్కడ K is equal to 1 అయితే అడిషనల్ స్టేట్కి వచ్చింది, అదే పాయింట్ ఎక్కడ రాస్తున్నాను, K is equal to 0 అయితే ఇటు వెళ్ళిపోతుంది, K is equal to 1 అయితే ఒరిజినల్ పొజిషన్కి వస్తుంది, సారీ లాస్ట్ పొజిషన్కి వస్తుంది. Okay, once you reach the S3 position, then we will go to the initial state. So therefore, the 10 states are reduced. 10 states are reduced to only 4 states. Therefore, how many number of bits that we are required for this one? How many bits are required? 4 bits are sufficient. Sorry,
4.
not 4 bits, 2 bits. Take that. 4 state.
Yes. 0, 0, 0, 1, 1, 0.
1, 0, 1. So therefore, 2 bits are sufficient. 4 states, hence 2 bits are sufficient for the memory element. That means 2 flip-flops. అంతే కదా, ఇందాక ఏం చేసాం మనం, ఒక మెమరీ తీసుకున్నప్పుడు హౌ మెనీ మెమరీ ఎలిమెంట్స్ ఆర్ రిక్వైర్డ్? 4 flip-flops are required. 1, 2, 3, 4, 4. Now it becomes only 2. అంతే కదా. So for the bit 1, bit 2. Okay, therefore that's how we can reduce the number of states also. Now we know, as in the first initial step that we have seen that once we have a state diagram something like this, we can convert into the SM chart. Shall we draw the SM chart for this one? Okay, so convert this.
సార్ అక్కడ కే వాల్యూ ఇక్కడ ఇన్పుట్ లేదు కదా సార్, అక్కడ ఇంక్రిమెంట్ కానీ కే చేంజ్ అవ్వడం కానీ ఎలా జరుగుతుంది సార్?
Again, tell me again.
సార్ కేకి ఇన్పుట్ ఏం లేదు కదా సార్, ఇంక్రిమెంట్ కూడా లేదు, కానీ అప్పుడు కే వాల్యూ కండిషన్ ఏంటి సార్? చేంజ్ అవ్వదు కదా సార్ అక్కడ వాల్యూ?
Yeah. So the moment, so this is actually meant for the control unit. ఇక్కడ control unit గురించి మనం చెప్తాం అన్నమాట.
Yes sir.
Okay. So what is happening here? We take the input of the shift register, okay, and counter is generated. Counter is generating to this one. It is internal to the circuit. Counter is automatically generating that one. So counter is suppose 0, 0 in the point, for example. Suppose some counter is something like this. I have a shift signal here. So it should produce the how many shifts? 4 shifts కాబట్టి 2 output, 2 bits ఉండాలా, అంతేనా? ఇక్కడ నాకేం జనరేట్ చేస్తుందంటే K అనే సిగ్నల్ జనరేట్ చేస్తుంది. If the shift value is equal to 1, SH is similar to that of clock signal, for example. Okay, shift 190. Okay, 190. అప్పుడే అవుతుంది 0, 0 ప్రొడ్యూస్ చేస్తుంది. K వాల్యూ అనేది 0 వస్తుంది, ఎందుకంటే మాక్సిమం కౌంటర్ రాకపోతే 0 ఉన్నట్టు అనమాట. That means we have to give the additional information inside of the multiplexers available in the shift counter. Okay, now if it is ఇంకొక షిఫ్ట్ జరిగింది, then this becomes 0, 1. Again the count value is equal to 0 only. ఇంకో కౌంట్ అప్లై చేశారు, ఇంకో షిఫ్ట్ వచ్చింది, నెక్స్ట్ ఇట్ విల్ చేంజెస్ టు 1, 0. అగైన్ దట్ వాల్యూ ఇస్ 0. సో ఇంకో షిఫ్ట్ వచ్చింది, దెన్ 1, 1 వచ్చింది, దెన్ ఇట్ బికమ్స్ 1. Okay, so therefore what you are asking that, so the K is inside of the module, it's not external. Yes, it is not external, it is inside of the circuit only. Okay, it is not at all externally exposed to that one. Okay.
Okay.
Next, we consider this one. How do we convert this one into? So this is the diagram that I can tell. So I think it's self-explanatory. No need to explain this one because మనకి diagrams తెలుసు కదా. So you can see here, this is the diagram. So time is up now. Okay, just can you wait for 1 minute? I'll complete it. Okay, please consider this. So the same diagram. So first నేను ఈ స్టార్ట్ క్లాసింగ్ లో నేను చెప్పాను ఎట్లా మనం ఇది చేయాలనేది. ఓకే, ST load, S1 M, SH add, SHK, all these things can be self-explanatory. Okay, so the first starting లో నేను చెప్పాను, ఆ విధంగా మనం కన్వర్ట్ చేస్తాం. ఓకే, నెక్స్ట్ based on this diagram, based on this SM chart, okay, we are going to write the Verilog program. So So we have tried the Verilog program for this one. We will see that one in the next class. Okay. See control unit key, especially this the multiplier control unit. So we have to write the multiplier control unit for this one and generate the truth table for this one. First of all, we have to generate the truth table or state transition table. State transition table. First we have to draw, and second Verilog program we have to draw. The third one is implementation. Third one is implementation. So these things we will see in the next class. Okay. So thank you very much. I will see that in this in the next class.
Sir, recordings upload చేయండి.
చేస్తాను.